This is Sachin.
This is Amitesh.
We are presenting on effective WiTech identification using deep transfer learning with SNR as an additional feature for AI Simutus 2021. In today's world, the spectrum is congested due to the presence of many devices communicating simultaneously. This happens at both public locations like metro stations, streets, and industrial locations like factories. Spectrum is sensed by both user devices such as mobile phones and laptops and industry devices, as well as mobile network operators at base stations that communicate to them. Effective sensing of wireless technology is critical in today's congested wireless ecosystem for effective utilization of limited resources. So as you can see from the figure on the left, the spectrum demand has escalated exponentially over time with next generation devices and high bandwidth applications, and the spectrum is very congested right now. There's ineffective use of spectrum, and spectrum has increased usage increased in all of 2G, 3G, 4G, and also Wi-Fi. So the ever increasing demand for data may soon congest Wi-Fi networks. So dynamic spectrum sensing is another application envisioned by the 5G standard that requires sensing and switching spectrum. So in the process of mobile network operators moving from 4G to standalone 5G networks, 5G networks should be operated in non-standalone mode or 4G networks over the same frequency band to meet the requirements of spectrum sensing. So rapid spectrum sensing for demand-driven spectrum allocation between 4G and 5G is an essential part of this rollout process. So these are the two problems we want to address using uh, deep transfer learning: how to perform dynamic spectrum sensing, and also how to solve the issues of today's congested wireless ecosystem. So we move on to the problem statement. The aim is to train a single network with large enough accuracy but small enough size for practical applications. These are contradictory in nature and subject to the below issues. What format of samples needs to be used? IQ time series or FFT IQ frequency bills. Each of these series appears in real, imaginary phase, linear magnitude, decibel magnitude, or combination of them. Secondly, what neural network architecture, LSTM, RNNs, CNNs, FNNs, FCNs would work best for what format, and its complexity in terms of number of layers and neurons. In a little more depth, so we have 128 sample snapshots of complex signals belonging to the three different Wi-Fi technologies of Bluetooth, Wi-Fi, and Zigbee with different signal to noise ratios in both IQ time series form and FFT IQ frequency bins. All snapshots can be viewed as is or put in different forms or combinations of them or even plotted as images. So the aim is to pick a data format and train a single neural network that can classify these signals for practical applications like dynamic spectrum management and hardware implementations for spectrum sensing in mobile phones. You can see the spectrum mask in the picture here and the different channels, so the different uh, technologies in the other picture. So description of the dataset used for our paper. So we use the Crawdad's OWL interface dataset. So this is a 5-dimensional tensor of the below structure. So there are 15 labels corresponding to this 15 label channels of different technologies of 12 channels of 10 channels of Bluetooth, 3 channels of Wi-Fi, 2 channels of Zigbee, then 21 SNRs, 715 snapshots of each type, and there are 128 samples in each snapshot. And of course, IQ represents the 2 dimension. So Spectrum sensing could be performed at various stages of the downlink data processing as shown in the figure. Radio signal sensing for technology identification can be done at acquisition as a temporal signal, or after hardware processing as a frequency domain signal, or after software processing as a decoded signal. So this is conventionally done at the end of the pipeline. Decoding the signal could be sped up significantly using deep learning algorithms, saving a large amount of energy. So as you can see, wireless technology data is available as time domain representation and frequency domain representation for the same snapshot. Conversion to the frequency domain requires additional processing at the hardware side and is more time consuming. In addition, that wireless signal can be represented as real, imaginary phase, linear magnitude, decibel magnitude, data series, or a combination of them. So the best format needs to be selected for classification. A combination of these can also be used for any classification, especially with CNNs and LSTMs that can extract features from multidimensional inputs. So popular combinations include FFT IQ data in 2D form, IQ time series in 2D form. So deep transfer learning across SNR. So another important aspect of sensing radio signals is that they appear at different signal tonizations based on the noise level and device density. A model designed for particular SNR may not work for a different SNR. So SNR is an important feature to consider while designing a model for wireless technology identification. As you can see from the image that there are 21 SNRs, and as you move from -20 to +20, the signal gets clearer. So we propose a novel approach to wireless technology identification using deep transfer learning across SNR to outperform conventional methods. So wireless signals at different SNRs need different strategy for efficient classification, and SNR is a time-varying feature in wireless technology data that provides an additional degree of freedom. This is because SNR varies both as a hardware device moves spatially and temporally. So as I mentioned earlier, a model that works with signals having a high SNR may not perform well with signals that have a low SNR. We study the concept of how transfer learning can be leveraged to design neural networks that work across different SNRs. In particular, we study questions like whether a neural network pre-trained on high SNR can improve the performance of low SNR data. So as you can see the image on the right, we train the learning system with high SNR and transfer the knowledge to lower SNR, to specific lower SNR. So this is deep transfer learning across SNR. So this is the introduction and the different data types and the problem statement in detail. So what are our main contributions in the paper? We show that fully connected neural networks and convolutional neural networks work best for classifying frequency domain data, and long short-term memory networks work for time domain data. Secondly, our experimental results show that leveraging transfer learning can give additional gains of 4 to 20% in accuracy depending on the SNR of the signal. Over to Amitesh for the remaining part of the presentation.
Okay, types of neural networks. Neural networks are used to learn complex nonlinear functions from inputs to outputs for performing powerful tasks like classification or regression. The neural network architecture that would work best for each wireless signal format needs to be matched from the popular types of long short-term memory (LSTM), convolutional neural network (CNN), and fully connected network (FCN). LSTMs are well suited for classifying, processing, and making predictions on time series data. FCNs would work better for frequency domain representations as the data is compartmentalized into bins. CNNs are expected to work best with IQ signal data series in the frequency domain as they expect two-dimensional inputs. CNNs have been used rigorously for image classification tasks and are being recently extended to the wireless signal domain. Next slide. Selecting the wireless data format. The type of neural network that would suit each data type varies from the one available in its literature. We begin our simulation study by understanding the various formats of wireless signal data in relation to neural networks by classifying them with simple baseline FCN. Moving down the rows of table 2, we observe that the real and imaginary parts of the FFT lead to very low accuracies of about 20%, implying that they don't contain sufficient information for classification by themselves. The accuracy for the phase part of FFT is almost 1 by 15 times the magnitude part, implying that it is uniformly distributed over labels and is least useful for classification out of the 5 FFT data series. We can infer that the information in a frequency domain signal is mainly represented by its magnitude and not its phase. Looking at the second half of table 2 containing the time domain data series representations, we notice that the accuracies are extremely low. These are better classified with LSTMs and not FCNs, as LSTMs can model temporal correlations. This also indicates that when a 2D convolutional neural network is to be used, the FFT data in the IQ form or phase magnitude form would work best over IQ time series data, as CNNs are not able to capture temporal relations well. Another important observation we make is that now the magnitude part of the IQ data as compared to the phase part is uniformly distributed, implying that the information in a time domain signal is mostly represented by its phase and not magnitude. Next slide. DifferentNN structure. The complexity in terms of number of layers and neurons and different hyperparameters needs to be determined as well. The higher the complexity of the neural network, the higher the accuracy. But the time required for classification also increases. So a balance of complexity and time needs to be achieved to ensure the practical applicability of the neural networks that are trained. The best classification is for the FFT magnitude, since most wireless technology features evidenced by the frequency bins. Since FFT magnitude works best, we continue our exploration with that format for FCNs by varying the hyperparameters and training the model. Table 3 contains the results so obtained, and proposed FCN model is shown in table 4. Next slide. The results are as follows. Table 4, 5 and 6 represent the LSTM, CNN and FCN model structures used respectively. The results from table 7 shows that accuracies for the low SNR split differ from that of higher SNR split by over 10%, implying that SNR has an influence on wireless signal classification. For example, the accuracy changes from 83% for low SNR to 96% for all SNR. So in-depth investigations are performed at each SNR specifically to truly understand the nature of wireless signal data and the adaptability of neural networks across this new dimension of wireless signals. Next slide. So here we explain the transfer learning across SNR. SNR has a significant impact on the performance of the deep learning models, as models trained on low SNRs would not work as well as those trained on high SNR data. Moreover, a deep trained learning model is more likely to perform better for high SNR inputs over low SNR inputs. As expected, the accuracies at lower SNR is lower, with the value starting to drop beginning with 0 dB, that is for negative values. There is a drastic drop in accuracy at minus 12 dB, as you can see in the graph shown in the figure. Models trained on the low SNR split seem to have worked reasonably well at the high SNRs, but models trained on high SNR split work poorly at low SNRs and break down below minus 12 dB. For the lowest SNRs of less than equal to minus 12 dB, the models trained on the low SNR split seem to work better than the models trained on all SNRs, implying that the need to train models specifically for these lowest SNRs. The reason behind this observation is that deep learning models can learn more generalized patterns at low SNRs, but only specific patterns from high SNR data. This calls for the need to learn specific weights or models to improve the performance of neural networks for specific SNRs, which we do through the process of transfer learning described in next section. Next slide. Transfer learning improves accuracies across all the SNRs in figure 6 for all pre-trained models by modest values of 4 to 5%, showing that transfer learning is effective in improving the performance of deep learning for wireless signals. Transfer learning seems to be the most effective, with LSTMs followed by CNNs and FCNs. The gain increases to 10 to 20% for the lowest SNRs for all the three models. In particular, when pre-trained LSTMs are used, additional gains of 10% are witnessed. In general, neural networks pre-trained on low SNR split gives the best performance with transfer learning. However, FCNs are different in the manner that pre-training on the low all SNR split gives larger gains over the low SNR split, showing that LSTM and CNN can learn generalized patterns due to their more complex structures.
Further work. So the goal is to extend this conference paper to AI journal or IEEE journal. In order to do so, you want to derive some information theory explanation as to why deep transfer learning across SNR works, or extend to more complex data formats like the spectral coherence function. Thank you.